Right. So let's, as always, start with a quick recap of the points that we discussed in the last lecture and the important applications of that. So in the last lecture, we were again looking at basically applications of, still few more people coming. So we were basically looking at applications of the triangle law of vector addition, where we saw that the magnitude of the sum of two vectors is given by this formula, square root of e square plus b square plus 2ab cos theta, and the angle between the resultant vector, which is the sum, and the other two, and the vector e is given by tan alpha equal to b sin theta upon e plus b cos theta. Now we saw that when we are adding, when we are using the triangle law for the summation of the two vectors in general, there are two kinds of situations that come up for angle. Okay, so one situation is like this, that if vector E is like this and vector B is like this, then you can see that the angle between them is an acute angle, because this is the direction of vector A, this is the direction of vector B. So the angle theta over here is an acute angle. Okay, but there's also a situation where something like this could happen, where the two vectors we are dealing with are in such directions. So we could also have a situation like this, where the two vectors we are adding are in directions like this, so that if you look at their mutual angle, how they are related to each other, this is the direction of vector E, and this here is the direction of vector B. So changing from this direction to this direction, the angle you are going through is theta like this. So in this case, theta becomes an obtuse angle. So in general, we have to learn how to replace the value of cos theta and sin theta in these equations for both the cases, theta being acute angle as well as theta being obtuse angle. And to that end, we had seen the most important part of last lecture, which was about the application of trigonometric functions in second quadrant. So the second quadrant formula for theta being in the second quadrant means greater than 90 degrees but less than equal to 180 degrees. That is this situation, the second situation over here, this one. So for that, the formula we had seen was like this, that cos theta is equal to minus of cos 180 minus theta, whereas sin theta is positive of sin 180 minus theta. And if required, but we don't need at this section, tan theta is again negative of tan 180 minus theta. So this is, you can say, it's coming from the ASTC rule, or more importantly, this is coming from the method of projections that we had seen. Okay, so the quadrant 2 formula that we had seen, that had come from the method of projection. Okay, to define the sine, cos, and tan. Okay. So this is something that if you are still not 100% confident about, you should go through a review of my previous lecture section on this also. Maybe you will need to go through a review of that a couple of times before you're 100% confident, but we'll be doing a lot of problems also, so this will become clear. And today we'll also continue ahead by understanding this in the other two quadrants, so that we are clear about any theta between 0 and 360. But as far as the formula of the triangle law above is concerned, as far as this formula is concerned here we never substitute theta in the third or fourth quadrant. It is either acute angle, so it's between 0 and 90, first quadrant, or it is obtuse angle, so it is between 0 and 180. So these formulae are enough over here. So just as a quick example of this formula, you can see that if I apply this formula over here, for example, cos of 135 degrees will become minus of cos 45. That will become minus 1 by root 2. But for example, sine of, let us say, 127 degrees will become will become positive of sine 53 degrees. So that will be positive of 4 by 5. Okay. So these are just two quick examples of how we use these formulae. So now let us look at an example where we are going to directly use this formula for calculation of a vector problem. Okay, so let's look at next thing. Let's look at a vector relation problem. So for example, we are given some vectors in relation to an XY system like this. So in this, I have, let's say, given vector E as something like this. And let's say it has a magnitude of 7, whereas vector B, I'm now showing vector B like this. Let's say this is my vector B. And its magnitude is 5, but also this angle here, it is 53 degrees. Okay. So now I want you to state two things in this over here for me. One is find the angle between the vectors A and B. Okay, state the angle between the vectors A and B. And secondly, if R denotes the vector sum of A and B, the resultant of A and B, then find magnitude of that vector and the vector R's angle with respect to the x-axis. So as a review question of what we've done last time, let us work out this question, and also we'll see that this type of question is there in abundance in your second worksheet. So with some of these review questions, you will automatically understand how to tackle those questions also. Though I will be coming to the worksheet problems also, but today I will be coming to the worksheet questions, a few of them for hints and discussion in the last part of the lecture. Whereas my fourth session of vectors, which will be the next one, that will be more like a problem solving session. So we will fully discuss each and every question of worksheet 2 and also today's worksheet, which I give you later, worksheet 3, plus few more problems. So you can also, in case things are not working out that well for you in terms of the worksheets, you can just wait till session 4. Till then, you keep trying the problems, keep taking hints from me. But in session 4, I will do a full discussion of a lot of problems. So you can wait till that. Anyway, so let's start this problem. Just work it out. Just try this out yourself. You can send me the answers for the first part. So again, for those of you who might have joined late, just to remind you that this is a recorded session. So you don't need to worry about the earlier part which you missed. It will be there fully in the recording, which you will receive. So just try this out, people. Tell me the answer to the first part. What is the angle between the vector E and B? I'm waiting for your messages. Right, so let me help out with the angles. So as I said that, the vectors are always movable items like this. So you can just pick up this vector A and draw it somewhere else, and in relation to that, draw the vector B. So if I just readjust how I've made the diagram here, you will realize that the vector E and the vector B have this kind of a relationship between them. Suppose this is the direction of vector E. So E is like, let's say, pointing towards the east, like this. Now in relation, where is the vector B? The vector B is pointing somewhere towards northwest, such that it's like this. The vector B is somewhere here. Okay. And given to us is that this angle is 53. But remember, this is not the angle between A and B. And in this case, as you can clearly see in the diagram, the angle between A and B, this is the direction of vector A, whereas this is the direction of vector B. So to turn from the direction of vector A, which is this, to the direction of vector B, this is the angle that I'm looking for. So that theta, you can see, is 180 degrees minus 53. Just the value we were talking about just now, a while back. So it's 127 degrees. So that is the answer to the first part. The angle between A and B is 127 degrees. Okay. Hope this is clear to you. So you can see it's the same diagram that I've repeated, okay, but only I've placed the vectors closer to each other. I've placed it head to head like this. So that is easy for me to understand in the diagram why that angle is like this. So this is the first important thing, that given two vectors which are just drawn arbitrarily anywhere, you should be very clear in your understanding of what is the angle between the two vectors. And the way to get the understanding is how I showed you, by redrawing the two vectors, against each other, so that it's very easy to identify what is the angle involved. Okay. Now next, to find the magnitude of the resultant, let us just apply the triangle law formula. Okay. So if I just apply the triangle law formula, it is given to me that the magnitude of the vector E, which I can just denote by E, that was already given to me in the question, that was how much? 7. And the magnitude of the vector B, which I can denote with a short symbol B, is given to me in the question as 5. And the angle theta I have just found out to be 127 degrees. Okay. So magnitude of the resultant of A and B will just become root of A square plus B square plus 2AB cos theta. Now in this, when I am substituting cos theta, I have to basically work this out. It is cos of 127 degrees. So I have to apply the second quadrant formula, which we were just discussing about. So that is minus of cos theta minus 180. 180 minus theta. So it is minus of cos (180 degrees minus theta), and theta here is 127. So that becomes minus of cos 53. And from your common knowledge of triangles, we know that this is minus of 3 by 5. Okay. So that is what we will substitute this as. Okay. Whereas other things, let's look at. So this becomes root of 7 square plus 5 square plus now 2 into 7 into 5 into minus 3 by 5. This is what we do. So now we are in a position to just algebraically solve this. So 49 plus 25, and the minus sign, just bring it out now. So this becomes 7 into 2 into 3. Okay. So minus 42. Is that okay? Just check what I've done over here. Alright, so this will now finally become how much? 49 minus 42 is 7. So 25 plus 7 is 32. So that is 16 into 2. So 4 root 2. You can see will be become the magnitude of. So I'm just minimizing this so that you can see the solution in context of the diagram we made earlier. iit, I jump here. Alright people, so hope that is clear so far. So back in the triangle, actually what we are doing here is we are calculating this third side, but we are not calculating it by using any geometry and all that. We are just using the formula for the triangle. So this third side only is the resultant of A plus B. So this one's magnitude only we are now getting, because we are already using the information that this one's magnitude is 5. This one's magnitude was 7. And now this one's magnitude was unknown. So that is coming out to be as how much? It's coming out to be 4. Now the other thing we want to do now is we also want to calculate this angle. We wanted to find out this angle alpha. So that's the second part of this. So that's where we'll use the tan alpha formula. So if you're clear with this, now we can go ahead and see the second part of it. To calculate the angle alpha, we can now use this formula. That tan alpha is b sine theta upon a plus b cos theta. Now in this formula, cos theta we had already seen. I'm just repeating the value. That is cos 127 degrees. That was working out to be minus 3 by 5. Now similarly, sine theta, this is the same value as we had done earlier when we were revising about the angles. So this actually becomes positive of sine 53, because sine is positive in the second quadrant. So it is plus 4 by 5. Just a quick correction here, this is 3 by 5, not 3 by 4. So now substitute these values, and of course b was 7 and e was 5. So substitute that over here. So we get tan alpha is b, that is 7 into sine theta, which is 4 by 5, divided by a plus, so that is, oh sorry, b is not 7, b is 5, a is 7. So anyway, so this is 5 and this is a, which is 7, plus now this term becomes 5 but into minus 3 by 5. So you can see that this actually becomes 4 upon 7 minus 3. So that's actually 1. So interestingly, the value of alpha comes out to be 45 degrees. So that is a complete description of our resultant. So this is what we are expected to be able to do by using the triangle law. How we can manipulate the triangle law to find out the sum of two vectors, both in terms of the magnitude of the resultant as well as in terms of the direction. Okay, so we need to understand this calculation fully, the second part. Okay, so most of the questions of the worksheet 2 that I had given, when I discuss with you the hints later today, you will see that we are just using this kind of principle. This is all we are using. Entire worksheet 2 almost is just application of this kind of algebraic formula manipulation, or just making use of the triangle and solving it geometrically, whichever is applicable in whichever question, but that's all there is to it. Okay, now let's move on to what we want to study today. Okay, this is recap of last time. So the discussion today starts with understanding trigonometry in all 4 quadrants. So since we have already done quadrant 1 and 2, quadrant 3 and quadrant 4. So Q1 all, Q2 sine, Q3 tan, and Q4 cos, ASTC, that one. So we will continue ahead with our understanding of that. So let us take quadrant 3. So the angle we are talking about is in the third quadrant here. So it is greater than 180 degrees and less than equal to 270 degrees, like this. So our vector diagram or our projection diagram now is looking like this. If we have actually rotated our so-called rod, a standard rod, to an angle which is in the third quadrant, it will be placed like this. So remember, this is our rod of unit length, the standardized one. And in this diagram now, this whole angle from here to here, this angle is theta. So for example, suppose theta is, let us say, let's say 225 degrees. So basically it is 180 plus 45. Think of it like this. So this is how this would look like. Now in this diagram, first of all, let us understand how the projections would be looking and how we can simplify it further. So just zooming in a little more on the diagram, you can see that if I drop a perpendicular like this onto the x-axis and a perpendicular like this onto the y-axis, then now this represents our x and this represents our y. So this projection over here, it represents our x, which we can see is negative because it's lying along the negative x-axis. And this projection here, you can see is our y, which we can see is pointing in the negative y direction. So y is also negative. Okay. While of course our the length of the rod is the standard thing, so it's unity. Always sticking with that. Okay. Now we can see another thing over here, that if we look at this angle, this small angle over here, and denote it as alpha, then this becomes a useful right angle triangle for us. So first of all, that alpha you can see is nothing but theta minus 180 degrees. So for our above example, where we have taken theta is 225, for this example, our alpha becomes 45 degrees. Okay. Now this smaller right angle triangle, let me just bring it out and make a separate diagram of it. So that right angle triangle is looking something like this. Something like this. Or go at this side. And this third side, this one, is the unit length of the rod. And this angle here is alpha. Okay. Now just as far as triangle is concerned, how much is this side? It is magnitude of x. It's just a side length. So we are now in the triangle, we are not bothered about x being negative, y being negative. We're just concerned about the side length. So from this triangle, we can see that the side lengths are mod y and mod x. So just apply the normal trigonometry over here to the triangle. So mod x upon the length is nothing but cos of alpha, because it is based upon hypotenuse. Okay. And of course, L is unity. So that means mod x is cos alpha, okay, because L is unity. Similarly, in the same triangle, you can see mod y by L is nothing but perpendicular upon a hypotenuse. So it is sine alpha. And again, using the fact that L is a unit length, mod of y is becoming how much? It is becoming sine alpha. So in my above example case, it is becoming cos 45 and sine 45, which are 1 by root 2. Okay, because this is that right angle triangle. So this triangle, this one, is I've just picked out this triangle from the original quadrant diagram. So now that I have mod x and mod y, what I can do is I can understand what x and y individually are. Okay. So from this diagram, we can see that x is negative and y is also negative. That means x with sign should be negative of its mod and y with sign should be negative of its mod. So all we do is in this, now we import these values. We have got mod y and we have got mod x. So just substitute them over here. So next step, just substitute these values over here. So we are getting x is equal to minus of cos alpha and y is equal to minus of sin alpha. And remember, in our trigonometry definition, x is nothing but cos theta. So cos theta is becoming minus of cos alpha. Or we can say that cos of theta, when theta is in third quadrant, is minus of cos theta minus 180 degrees, because that is what our alpha was about. And similarly, sin theta is minus of sin alpha, because it's minus of mod y, and mod y is sin alpha here. So that means our ultimate formula is becoming that sin theta is minus of sin theta minus 180. And then just divide these two and you get the formula for tan. So tan is sine upon cos. So it becomes minus of sine upon minus of cos. So that's positive only of tan theta minus 180. So these become our relevant formulae for quadrant 3. Okay. So I'll just minimize all this so that you are able to understand the derivation of the formula. But as you can see, it is basically just it's just the same thing repeated for third quadrant like we done last time for fourth quadrant. So I'll bring you to the steps below also, but first just observe these steps carefully, and better is if you practice them out yourself a little bit also. Right, so I'm just scrolling down to the last part. So you can see ultimately these are the formulae we use in third quadrant. Just like the formulae for second quadrant we had discussed in the previous question how to apply them. Now this is how we apply formulae in the third quadrant. So let's now do a use of these formulae. So let's do a quick exercise here. Find the values of the following. Cos of 240 degrees. Sine of 210 degrees. And also let's find out tan of 225 degrees. So after you absorb these formulae properly, how they have come. Now just apply these formulae to find out the values of these 3 questions I've given. So I'm waiting for your replies on chat. Yes, anyone solved them? Please put up the values if possible. Yeah, I'm getting some answers. Let me see. Likit, you gave the answer to the first one, right? Cos 240. That is correct. Good. Likit, your answer is correct. Okay. Good. Yes, Dhrumi, correct. Okay, good, Ishika. Dhrumi, check your answer for the second one. Is it correct? Yes, it's correct. Yes, Ishika, correct. Ishita, sorry. Correct. Both answers correct so far, people. What about the third one? Correct. Ishita, all your 3 answers are correct. Good. All right. So cos 240, I'll just use this formula. It is minus of cos. Now in third quadrant, we express the angle as theta minus 180. So 240 minus 180 degrees. So that becomes minus of cos 60. And cos 60, you know, is half. So this becomes minus half. Okay. So if the angle we are talking about is 240 degrees, then its cosine is equal to minus half. Similarly, you'll see sine of 210 will exactly come out to be the same value. This will be minus of sine, because third quadrant sine is also negative, but theta minus 180. So 210 minus 180 degrees. So that is minus of sine 30 degrees. Okay. And sine 30, as you know, is half. So using that value, it is minus half. And similarly, tan, but the only difference is tan in third quadrant is positive. So when we are calculating tan 225, the sign will be positive, but it will be again expressed as theta, that is 225 minus 180. So it becomes positive of tan 45 degrees. So it's unity plus 1. Okay, so this is the application of the formula for the 3 questions. Okay. Okay, good. Likit, your answers are correct. Dhumi, you got it correct. Ishita, you're getting it correct. So good. So now you people are getting an idea about how we apply the ESTC rule using the projection formula. Now let's come to quadrant 4 and finish this off. So as you would have guessed, in quadrant 4, we are talking about theta such that it is greater than 270, but less than 360. Okay. But actually, in a sense, this is a very twisted way of expressing the angle. In quadrant 4, we usually express the angles as negative values, because anti-clockwise of some angle like 300 is the same thing as clockwise of 60, or anti-clockwise of 330 is the same thing as minus or clockwise of 30, like that. So anyway, let's see how it looks in the diagram first. So this is what I meant, that there's a very twisted way of expressing the angle as this. Easier way of expressing the same angle would be to say, instead of it is anti-clockwise of so much, it is clockwise of this much. So clockwise with sign convention, we just put a minus sign. So that's why typically in the fourth quadrant, though we are studying it like this, we don't express the angle as this way. We just express it as minus of some angle. Okay. So for example, if I have theta equal to 300 degrees, it is the same way we can express it as minus 60 degrees. Saying minus 60 expresses the same thing because this angle is a minus 1. Okay? So here we will now actually denote this angle as alpha, and we will see that alpha is actually equal to, just as the magnitude of alpha is concerned, it is equal to 360 minus theta. But remember, alpha is clockwise. That's why I put it with a minus sign here, because it's clockwise. And but in this case, I'm just reporting its magnitude, so it's just that much. Okay? Now, when you drop the perpendiculars on this, you can see that this unit length, it is throwing a positive x projection. So x is positive, but again it is throwing a negative y projection. Okay. So our x, which remember is nothing but cos theta, should be a positive quantity. So our y, which is our sin theta, should be a negative quantity. And again, the ratio of x and y is the ratio of positive and negative quantities, so that should be negative. So that is why in quadrant 4 it is ASTC. C is positive, cos is positive, sin and tan are negative. So that's the basic idea. Now let's again look at how to calculate the values. So I'll just quickly repeat what we've done earlier and understand this fully. Okay. So if our standard rod of unit length is over here now, okay, then our so-called angle theta was this one. Okay. But more importantly, we identified that this angle here was alpha, where alpha is 360 minus theta. Okay. So when we drop this perpendicular here now, we can see that here we are getting a right angle triangle where this side has just a side length is mod y, because that's the same as this thing here. So the magnitude of this side length is just mod y, and similarly the magnitude of this side length is just mod x. So again you have the same thing, that mod x by L is equal to cos alpha, mod y by L is equal to sin alpha. And remember, L is unity. We are dealing with that. So very simply, you can see that this tells us that the magnitude of x is cos alpha. This tells us that the magnitude of y is sin alpha. So we understand that as far as algebraic sign is concerned above, x has a positive sign and y has a negative sign. So x will become positive of mod x. So that means x is nothing but cos theta. That will become a positive of cos alpha. Or we have the formula that cos theta is plus cos of 360 minus theta. Okay, so this becomes the cos formula for the fourth quadrant. And similarly, y is a negative quantity, so it's minus of mod y. So y is replaced with, sin theta. And on the other side, mod y is replaced with sin alpha. So you can see that sin theta is nothing but minus of sin alpha. So this formula becomes sin theta is minus of sin 360 minus theta. That's it. Very simple. And then if you just divide these two equations, you will get your tan formula. So tan is negative divided by positive. So negative of sin by cos. So tan. So this becomes the third formula. Alright, so these are our quadrant 4 formula. So I'll quickly minimize this and full perspective of it. So finally, these are our formulae. Right, so now you have the formula for all the 4 quadrants, and through the 4 quadrants projection method, you can understand the logic of both the algebraic sign of sine, cos and tan, ASTC, as well as the actual values, how we do it. So you will get plenty of practice in the application of this through vectors only. So I'm not going to do too many more problems just about calculation of sine and cos. Rather, now we will come to one very important aspect of vectors, which is expressing vectors in the second form, which is called the component algebra. So far, whatever representation of vectors we have done geometrically, but now we move on to the next part, where we see we are going to learn how to represent vectors by what is called the component method. And once we learn to represent, we'll learn to do all operations, including more operations now, like subtraction or addition of more than 2 vectors, things like that we'll learn how to do by this representation. So now we look at the next aspect of vectors, that is representation of vectors in what we call component form. So basically in component form, or what we call component algebra of vectors, we represent using a Cartesian coordinate system. Yeah, a system of Cartesian coordinate axes. So today we will be discussing the representation in 2-dimensional system. So we'll consider only the x and y axis, but eventually we'll also be discussing in 3 dimensions. So the first aspect of it is that we define some kind of coordinate frame. In this case, we are still sticking to 2-dimensional. So our coordinate frame is 2 mutually perpendicular axes, which are the x and the y. Okay. Now the second thing we define in this is something called the base unit vectors. So this is very important. Okay. Or they are also called standard unit vectors. So you'll understand very soon that these are used to actually represent. Just hang on a moment, people. I'm getting a bit of lag in my whiteboard, so I'll just reload the software. Just one moment. Should be good now. Let's see. Okay. So we define, going back here, something called standard or base unit vectors. So these are two special unit vectors which are given specific names. Okay. I cap is the standard symbol that we use for, remember what a unit vector was, it's a vector of magnitude 1. But I cap is a special unit vector. It's a unit vector which has a specific direction, and that is, it is along the positive x-axis. So it's a unit vector that points along the positive x-axis. So I cap is a vector that looks like this. Doesn't matter where we draw it. We can draw it here, we can draw it here. As long as our direction is correct, it's pointing along the positive x direction. And as long as we understand that its magnitude is unity. So its magnitude is 1, and the specific name given to it is I cap. Similarly, we define the standard unit vector called j cap as the unit vector along the positive y-axis. And actually, we make use of these unit vectors I cap and j cap to represent a vector. So this is a unit vector, a vector of magnitude 1 along the positive y-axis. Okay. So this is like this. Again, it doesn't matter where we draw it. We can draw it somewhere else also. But as long as its direction is consistent and its magnitude is unity. So it's like this. Okay. Now, so once we have defined our x and y system, along with that, we have also defined our standard unit vectors or our base unit vectors. Now, any vector that we choose to represent, like for example, I'm just drawing a vector over here. This vector will be represented in terms of I cap and j cap. And let's see how it will be represented. So instead of drawing it as an arrow, I'll actually write the vector's value as an equation involving I cap and j cap. And when I write that value, it is called what is called component form of notating the vector, or component form of representing the vector. So any vector will be represented by an equation like this, that it will be some quantity which will be a scalar. So we denote that with ax because it's along the x-axis into I cap plus some quantity ey into j cap. Now in the diagram, what exactly is ax and ey I am coming to, but they are basically projections. But first let's understand the definition. So whenever we write an equation of this form, that we are writing the vector as something into I cap plus something into j cap. For example, we are writing it as 12 I cap plus 10 j cap, or minus 3 I cap plus 4 j cap, or any such things. We say that we are representing the vector in component form. Okay, so this is the vector E in what is called the component form. Whereas in the above diagram, when I have drawn the arrow, that is nothing but the vector A represented in geometrical form. So we have two interchangeable forms now. One is the geometrical form where we represent the vector by this arrow, and the other is the component form where we represent it by an equation. And in the equation, we have the term, we have the standard unit vectors I cap and j cap always. So here, the names given to these quantities ax and ay are very specific. Ax is called the x component. Okay, or we can also call it projection, and the name projection will make it clear what exactly it is. So it is the x component of the vector E, and similarly ay is the y component or projection of the same vector. And before you write all this down, we quickly understand this thing that ax and ay are not vectors, they are scalars. But you are multiplying ax over here with a unit vector, so it's becoming a vector. Ax into I cap is a vector, but ax on its own is a scalar. Similarly, ay into j cap is a vector, but ay on its own is a scalar. So ax and ay are scalars, okay, with either positive or negative sign. They have algebraic sign, but they are scalar quantities. Okay. Whereas ax into I cap, this is not a scalar anymore. This is now a vector, okay, along x-axis, because I cap is the unit vector used. Ay into j cap is not a scalar anymore. It's now become a vector because you multiplied the scalar ay with a vector. J cap is a vector after all. It's a unit vector, but it's a special type of vector. No? So ultimately, you're multiplying a scalar with a vector to represent it. Okay. So just minimize this and show the whole thing. Okay. So you can start with here representation of vectors in component form. So the first step when you are representing in component form is that you understand you are representing it using a Cartesian coordinate system. So you have to draw your coordinate system, or you have to at least fix the direction of x and y. Now in the standard reference, I have drawn x along the x-axis. I mean, I have drawn x along the horizontal axis and y along the vertical axis. But there's no hard and fast rule that we have to always do this. According to the convenience of our problem, we can take x and y anywhere. Okay. So let me just illustrate this point. So for example, we are looking at on a later day when we are studying, something like laws of motion or something. Let's say we are looking at a situation like this, that we have an inclined plane like this, and that inclined plane is smooth or rough or whatever, it doesn't matter. And we have something like a cylinder, okay, let's say, which comes rolling down the inclined plane. Okay, so we have a cylinder which is coming down the inclined plane, rolling like this now. Now in this case, you can see that the cylinder's motion is going to be along this axis, which is parallel to the inclined plane. It's going to be along this axis. So here, it will not be so convenient for us to draw the x-axis as like this and like this. What we'll do in this case, when we solve this problem later, is we'll define our coordinate frame like this, that our x-axis is actually parallel to this inclined plane, and our y-axis is actually perpendicular to the inclined plane. It will be more convenient for us to solve the problem using vector algebra when we do this, taking y-axis like this and x-axis like this. So it's not important that x-axis always has to be horizontal and y-axis has to be vertical. X and y-axis could be anywhere, but they have to be mutually perpendicular. So x, y are mutually perpendicular. That's the only thing. Otherwise, there's no foundation that it has to be horizontal and vertical. Anyway, so the first step is in component representation. We draw our x and y axis so that we are clear about what their direction is. And the moment we have selected x and y axis, we have also selected these two standard vectors. Because I cap, by definition, we cannot change this definition. It's a standard definition that I cap is always a unit vector pointing along the positive x direction, and similarly j cap pointing along the positive y direction. Now, once we have defined our I cap and j cap, now we can see that any vector that we want to write in the component form, instead of drawing an arrow, we'll represent it by an equation, where that equation is some component of projection multiplied by I cap plus some component of projection multiplied by j cap. So when we write the vector in this form, this becomes a component form. So for example, any vector written like this, I have a vector E, which is, let us say, 12 I cap plus 16 j cap. This is in component form. Or I have a vector B, which is, let's say, minus I cap plus 2 j cap. This is again in component form. So all these are examples of vectors which we are representing in the two-dimensional component form, because we are using only I cap and j cap. So that means only x and y axis. And as you can see, the quantities that I multiply with I cap, over here 12 and over here -1, they are scalar quantities which can have plus or minus sign. The quantity I am multiplying with j cap is again scalar quantity which can have positive or negative sign. So those quantities are called the components of the vector. So ax is called the x component and ay is called the y component. So I will just minimize this whole thing now so that you can take a quick look and a note of it if you want. And just remember these side note points, that x and y axis doesn't always have to be horizontal and vertical. They just, the important thing is they have to be mutually perpendicular. It's basically up to us how we select our x and y axis according to the convenience of whatever we are solving in our problem. Okay, people, so hope this point is clear to all of you. Right. So next up, let us understand what is in the diagram, what exactly is Ex and Ey. So if we come back to this being the vector arrow and this being the equation of the vector in component form. So what is the relationship between these two? Let's understand that. Okay. So we will understand Ax and Ay, that is the component, in terms of the magnitude of the vector, or what we simply denote as E, and theta, that is the angle with respect to x-axis. Okay. So now don't confuse the theta here with the theta in our vector addition. There we are talking about two vectors. So theta was the angle between the two vectors. But here theta is just the angle of a particular vector with respect to the x-axis. So basically we are talking in terms of trigonometry. What theta means for a given vector or a given direction with respect to my standard xy axis, that is my theta now. So it's the anti-clockwise angle made with respect to the positive x-axis. So keeping this in mind, let us now see the relationship between the geometrical representation of the vector and the component form. So if this is my x-axis and this is my y-axis. Now if I were to draw the vector in a more standard way, that is I want to start it from the origin. Instead of drawing it randomly somewhere over here, I pick up that vector and place it at the origin. So this is my vector E. So as you can see, this particular length over here is nothing but capital A, the magnitude of the vector. And this is the angle theta that I'm talking about. Here just for reference, I've taken this angle in the first quadrant, but the vector could have been over here, it could have been in second quadrant, it could be here, it could have been in third quadrant, whatever be the case. All the cases now we have understood geometrically. So from here, if we now drop a perpendicular on each of the axes. So we drop a perpendicular here and we drop a perpendicular here, just to make sure that these are just guidelines. So we represent them as dotted lines. So now the projection or the shadow that this vector casts along the x-axis, that is nothing but Ex. Okay. So back in this diagram, this quantity here, this length is Ex and this direction is along the x-axis. So we will represent this as Ex. We will represent this over here as Ey. And as you can see, the vector sum of Ax and Ay, Ax I cap and Ay j cap, is nothing but the vector E. So this is basically a triangle only, this triangle. So in this triangle, but it's a right angle one. So this part here, its length is Ax. So as a vector, I will represent this as Ax I cap. This is a vector. And this length over here is Ey from here to here. So as a vector, I will represent this as EY j cap. So this vector is placed here, this vector is placed here, and this sum over here is becoming this vector, as you can see. So that is why we write the equation that Ax plus EY. So that is why we logically write the equation that Ax plus EY, Ax I cap plus EY j cap is nothing but the vector. So the vector A, you can see, is the sum of this vector, which is nothing but Ax in length, but it's along the x-axis. So when we multiply that scalar quantity Ax with I cap, it becomes a vector along this direction of magnitude Ax plus this vector, which is again magnitude Ay but direction along y-axis. That resultant is nothing but this vector. Okay, but coming back to this diagram now, you can see over here that this is a 90-degree triangle. Now, this one, this triangle here, this is a 90-degree triangle. So we can just apply trigonometry here. So Ax by E is cos theta. So Ax becomes nothing but E cos theta. So this is what we had set out to do in the first place. We wanted to find out Ax and Ay in terms of magnitude of A and the angle it's making with the x-axis. Similarly, Ay by E by definition is sin theta. So that is why, given that we know E and we know theta, we can find out Ax and Ay by using these formulas. So these two formulae now represent our components in terms of the geometry, that is the vector E, its magnitude and its angle theta. Okay. So this is the most important thing, how to convert geometrical information about a vector into a component equation. So the components of a vector Ax and Ay in terms of the magnitude of the vector and the angle it's making with the x-axis. So these are the formulas. Ax is A cos theta and Ay is A sin theta. So using this, we can convert any diagram where the vector's magnitude is shown and the angle is shown into a component equation to represent the vector. And if you are asking why we are doing that, you will see next up when we study more things about components. Once we have got the vector in component equation form, it is much easier to carry out vector operations. Even sum of two vectors, which you have seen by triangle law, it is much easier in many cases to work it out by the component form rather than by the triangle law method. But of course, the triangle law method is more fundamental. That's why we started with that. Okay, so just make a quick note of this. So the last two relations here are the most important. Okay, that how to convert A and theta, that is magnitude and direction, or magnitude and angle, into the components Ax and Ay. Okay, people, so hope this is clear. Okay, now let us do a quick exercise first to learn the application of this. Okay. So express the following vectors A, B, and C in component form. Okay. Sometimes we also, instead of saying component form, we say I cap, J cap notation. The method of notation that we are using is I cap and J cap, that kind of notation. So now the information that is given to me is in terms of geometry. So the information that is, let's say, given to me is like this, that with respect to some coordinate frame, let us say these are my vectors. My vector E is like this. It's of magnitude 20, let us say, and this angle is 30 degrees. My vector B, let us say, is like this. magnitude is 25 and this angle, let us say, is 53 degrees, and the third vector is, let's say, like this, C, and its length or its magnitude, let us say, is whatever 15. So we have got all three vectors in the geometrical form. That is, we know their magnitude and we know which direction the arrow is pointing in. Now we have to convert that information into that I cap j cap notation or the component notation, where we express each vector as something into I cap plus something into j cap. So just try this out, people, and you can, when you're typing the answers, you don't need to write the whole equation. So you can just tell me, the x component and the y component. So for vector A, you can just write x comma y. So how much is x and how much is y? For vector B, x comma y. So you can tell me how much is the x component and how much is the y component. So hope this is clear so far. Anybody got the answers for A's components? How much is the x component? How much is the y component? Okay, like no, just be careful. Why should A's x component be negative? Because you see how A is pointing, it's in the first quadrant. So see, the thing is, it's initially a little confusing. So what you do is, you bring all the vectors when you're calculating them, you bring them to your origin. It will be just easier to work out. Okay. So let me just grab the vector A from there, just as if I have done that, and place it over here. Now you can see that the vector A, very simply, is of magnitude 20, I think, and this angle is 30. So for vector A, the magnitude is 20 and the angle is actually 30 degrees, nothing else. So your x component is A cos theta, which is 10 root 3 and not minus 10 root 3. Okay, that's the important thing. And your y component is A sin theta, which is 10. So the vector A is becoming 10 into square root 3 I cap plus 10 into theta. That's it. This is my answer. Okay. Now in the diagram, you can also verify that what we got is correct, because the way the vector is, it's the sum of these two components now, ax I cap plus ay j cap. If you see its projection on the x-axis, it is falling on the positive side. So that's correct. Its projection on the y-axis, it is falling on the positive side. So the projection is 10 root 3 on the x-axis, but on the positive side. And the projection on the y-axis is 10, and again it's on the positive side. Understood, Nalikit? Yeah, good. That's clear. Okay. Now do the same treatment to B and C, like I've done over here. Okay. Draw them in a separate diagram. Doesn't matter, it will take some time, but draw them from the origin. So that will give you clarity about, what angle theta is exactly and which quadrant it is lying in and all these things. We'll have 100% clarity about these things. Yes, but be careful about the sign, Ishika. Your answers should have some algebraic sign, and for B you have to be a little extra careful. Yes, Ishita, now it's correct for this. Alright, so let's apply the same treatment to vector B. And C is pretty obvious. All of you can see C is pointing downwards. So it just has a negative y component and does not have any x component. But even then we'll understand that properly. So there's no need to worry about how much time it takes to solve a problem. You just take all the time you require and neatly understand everything first. That's the more important thing. Now for the vector B, I should be mindful that it's in this sort of a direction. So it had a magnitude of 25. But more importantly, this angle was 53. So as far as the standard angle theta with the x-axis is concerned, that's this one. So theta is, so for B, the magnitude of the vector B, that is 25. But the angle with the x-axis is actually not 53, it is 180 minus 53. So it is my 127. Okay. So again you can see that I just apply the formula. Bx is B's magnitude into cos theta. So 25 into cos 127, which will actually become 25 multiplied with minus of cos 53. So minus b by 5. So minus 15. Okay, so that's where the sign comes in. Dx is this. Whereas dy is d sine theta. So just apply that same thing. So 25 into sine 127. Now second quadrant, remember sine is positive. So 25 into plus of sine 53. So 25 into 4 by 5 or positive of 20. Okay, so this is my b1. Okay. So now finally the vector b, you can see, is bx, which is minus 15 I cap, plus by, which is plus 20 j cap. And you can very nicely verify this in the diagram also, whether it makes sense fully. You can see that it does, because when you drop this perpendicular here and you drop this perpendicular here, you can see that the x component is this one. And the y component is this one. And they are having values which are negative and positive respectively. Dx is minus 15, dy is plus 20. That's how I'm getting this vector. So this is where the significance of trigonometry in 4 quadrants actually comes in. Very, very important. Okay, so I think this is clear now to everyone. Now, the last one is pretty trivial actually, but again, let us solve it using the proper logical method also. In this, if I draw the vector C, let's say this one, from the origin, if I draw it, be like this. So as far as the angle it is making is concerned, it's a very complicated angle. It might look like this. It's 270 degrees. Okay. So if you want to go with the proper formula-based method, cos 270, you'll have to write it as minus of cos 270 minus 180. You have to write it this way. That is minus cos 90. That is minus 1. Whereas sine of 270 is minus sine 270 minus 180. That is minus this should be 0. This should be minus 1. Just a quick correction. This value should be 0. So anyway, so your cos theta is 0, sin theta is -1. And what about the magnitude of the vector? We just saw. The magnitude of the vector is whatever it was, 15, I think. So 15. So the vector C will have x component, C cos theta. So that is becoming 0 because cos theta is 0. Whereas the y component is C sin theta. So C is 15 in magnitude, but don't forget that sin theta is -1, so it's -15. So in component form, the vector C will be written as -15 j cap. But you know, really, in this case, all this calculation is not necessary at all. You just understand that the vector has a magnitude of 15 and is pointing in which direction? The negative y direction. So the negative y direction itself is minus j cap. So anything that is pointing along the y-axis, whether it's positive y or negative y, its x component has to become 0. So that's why there's no I cap term. Or that's why Cx is 0. Whereas in this case, it's pointing along the negative y direction. So Cy is -15. So really all this is unnecessary extra calculation. We don't need all this. Okay? Just directly understand this. So this becomes conversion of the geometrical information about the vector into the component form. So once we have learned this conversion of geometrical into component form, next thing is we'll see how we can use component form to do algebra. Alright, so hope this is clear to all of you. So let us look at, now simultaneously let us look at addition and subtraction. In component form. And you'll see this is as easy as your regular arithmetic. And this method of doing addition and subtraction is as easy as regular arithmetic. So we have, let's say, a vector E written as Ex I cap plus Ay j cap. Just excuse me a moment, people. I'll again reload my software. This whenever the net speed gets slower, what happens is because of Zoom taking up so much computer resources. So all things which are already preloaded tend to create a lot of problems. Alright. So Ax I cap plus Ay j cap. Okay, this is there, and given another vector B in component form, so it is Bx I cap plus By j cap. Now we want to find out the vector A plus B in component form. So what you do is you've expressed A as this is your equation 1, you've expressed B as this is your equation 2. So on left hand side you're just adding the two left hand sides. So on right hand side also do the same. So just substitute the value of A in component form and then just use your normal algebra. Like so after substituting, you just open this bracket and you'll see that Ax and Bx have the common term I cap and Ay and By have the common term j cap. So you can just use that. And that's it. From that you can find this. So the sum of two vectors actually become the sum of the x components into I cap plus the sum of the y components into j cap. And this can now be extended to any number of vectors. So if we add A plus B plus C plus D like that, it's just Ax plus Bx plus Cx plus Dx like that. The summation of the x components into I cap plus the summation of the y components into j cap. So this becomes a very trivial and very easy way of solving for the sum of two vectors. So this is the equation that we get, or this is the formula that we get for addition of two vectors when we know them in component form. Now similarly, so you make a note of this, and similarly you yourself try to write out the formula for A minus B, okay, which I'm going to do next. But try to write it out yourself. Next, if I'm doing this operation, a minus b, just try to apply the same method and tell me what is the formula I get. And you will realize it's very easy, which is why the component method becomes the preferred method, particularly when we are dealing with more than two vectors, like we are going to do very soon now. Okay, so doing the same algebra now, you can see that your operation of a minus b will just become like this. Yes, Likit, that is correct. Good. So just substitute ax I cap plus ay j cap. This is your whole thing, is your vector a minus of bx I cap plus by into j cap. So this thing is your vector b, and then just apply the distributive property of the minus sign. So when you open the bracket, it becomes minus bx I cap minus by j cap, and this is plus ax I cap plus ay j cap. So when you finally take common, you have ex minus bx multiplied by the common term I cap, okay, plus ey minus by multiplied by the term j cap. So this becomes your formula of e minus b. So this is just for two vectors, and now we'll see that we can extend this to any number of vectors and do any combination of operations. Like we have vectors a, b, and c. We can calculate a plus b plus c. We can calculate a minus b plus c. We can calculate a plus b minus c. Any such combination can be done this way. Okay, so this is fairly straightforward. Okay. Okay, now let's tackle a quick question first using this. So suppose the vectors are given like this. The vector E is, let us say, 2 I cap plus j cap. The vector B is I cap minus 4j cap, and the vector C is 3I cap, or let's say minus 3I cap, for whatever reason is minus 3 plus, let's say, 3j cap. Let's just like this. Now we want to find all these things. Find the vector E plus B, then the vector E plus B plus C, then the vector B minus C, let's say. And as a mixed type of problem, let's also do the operation of E plus B minus of C. Let's do this. Give all answers in component form or in I cap j cap notation. So this is like as simple as your regular arithmetic. There's nothing at all difficult. Just you have to be careful of the algebraic signs. You know, for example, b के components क्या है? They are +1 and -4. So when you substitute by, make sure you substitute -4 over here and not 4. Yes, Dhruvi, your components of a plus b are correct. Good. Yes, so just minimize this little and solve it here. So if you write all the steps properly, your solution should look like this. Now, gradually, as you get more comfortable, you can start doing direct solution yourself without writing the steps. But initially, it's a good idea always to write the steps. Plus of b, which is I cap minus 4j. So now you can see when you take I cap common, you have 2 plus 1. And when you take j cap common, you have 1 plus of minus 4. So that becomes 1 minus 4. So this actually becomes 3 I cap minus 3 j cap. And this is what I was looking for. I was looking for the answer for a plus b in I cap j cap notation or in component notation. So this becomes my answer. Okay. So similarly, I'm just writing down the answers here, you can verify. So the second part, where I'm calculating a plus b plus c, and we just sum up all their x components. So plus 2 plus 1 minus 3, so that's 0. And sum up all the y components, that is 1 minus 4 plus 3, so that's again 0. So interestingly, their sum is a null vector. It's a null vector. Similarly, the third part, yes, for me that's correct. So, okay, good. Yeah, so the third part we want to do what b minus c. So let me just work out the steps for this one also. So b is how much? It is I minus 4j. And now we have to subtract from that. We have to subtract c, which is minus 3 plus 3. So this will become 1 minus minus, so plus 3 I cap plus minus 4 from here, and then again minus 3 from here. So it's becoming 4 I cap minus 7 j. This is what we should be getting for our b minus c. You can just verify my solving also. I believe it should be correct. So b minus c. So you can see 1 minus of minus 3, so plus 4, and minus 4 minus of 3. So that's minus 7. So that's the verification. That is correct. Okay. Similarly, you work out the fourth part. E plus B minus C. So that is our E was 2I plus J, plus B was I minus 4J, and C was minus 3. Sorry, there's a minus sign here. Careful. So minus of 3I, sorry, minus of minus 3I plus 3J. So with I cap we are getting 2 plus 1 minus of minus 3. So that's plus 3. We'll get 6. Right? With J cap we'll get 1 minus 4, then again minus 3. So this, as you can see, will become 6I cap, and again minus 6. So this is my answer for E plus of B minus of the vectors. Another type of operation we can do over here, something like this: E plus 2B. But ये करना है. So how do we do this? So again, very simple. You take the vector E, which was 2I plus J, and add to it the vector 2B. So 2 times B is 2 times I minus 4J. So this becomes 2 plus 2 for I, and 1 plus of 2 into minus 4. So that's minus 8 J cap. So this becomes 4I cap minus 7 J cap, or whatever. Okay. So this kind of operation can also be done. Any sort of combination like this can be just by using your normal principles of algebra, arithmetic. So I'll just minimize this so you can verify your answers. You can just add this last part. Alright, so just scrolling down for the last part. Yes, very good. 4 minus 7 is correct. Likit, to answer your question, how we got cos 53, that is actually a standard value you have to remember from now. Okay, so you just write down what I'm showing you over here. One of the standard right angle triangles you should memorize as part of your knowledge now is this 3, 4, 5 right angle triangle. This kind of triangle. If you draw a triangle, right angle one with the Pythagorean triplet of 3, 4 and 5, then it turns out that the angles are 37 and 53. So if this side is 4 or proportional to 4, so you can say 4x, this is 3x and this is 5x. So always this triangle will have this angle as 37 degrees and this angle as 53 degrees. And from that you can work out the trigonometry. So you can see, for example, that cos 53 is 4 by 5. Oh, sorry, is 3 by 5. For that matter, tan 37. So since we are taking 37, we'll have to take this as the perpendicular and this as the base. So that will become 3 by 4. This is just like, other triangles you have studied, like, for example, another standard triangle you have studied is the 30, 60, 90. So the 30, 60, 90 triangle has the sides in ratio. So if this angle is 60 and this angle is 30, then the sides are in ratio 2x, x and root 3x. So these are two very common triangles that we use in our physics applications. Similarly, a 45 one is much easier. It's x, x and x root 2 for the hypotenuse. So just keep this in mind. Okay. Alright, now we come to the next section of our component algebra, which is again very simple, which is that given a vector in component form, that is, let's say A is AXI cap plus AYJ cap. How to find the magnitude of the vector and how to find the angle it is making. So this is the reverse of what we've just done earlier. Earlier we've seen that we know mod A and we know theta. So we know that AX becomes A cos theta and AY becomes A sin theta. This is just the reverse of that, and as you must have guessed, it's pretty simple. If this is your vector E with respect to your coordinate frame, say like this. So now the idea is, I know this thing, it's EX, and I know this thing over here, it's AY. So I know the value of AX and AY, but what I'm trying to find out is this and this. So here, AX is a known quantity, AY is a given quantity, known quantity. I want to find out magnitude of A, I want to find out theta. You can just see, you apply Pythagoras theorem over here to this triangle. So magnitude of a vector becomes like the hypotenuse for its perpendicular sides. Very simple. And theta becomes such that tan theta is Py by Ax. So this is the reverse of what we saw earlier. That given Ax and Ay, this is how we find mod A and the angle theta. Then we saw that given the magnitude and the angle, how to find the components. So this is the interchangeability. You know the vector in one form, you can interchange it to the other form. Okay, people, so hope this formula is clear. So let's do a quick example problem. Find the magnitude of the vector A and the angle theta it makes with the x-axis. If we are given A part, let us say the vector is given like this. It is root 3 I cap minus j cap, and B part is I cap plus j cap, and C part is, let's say, minus 12 I cap plus 16 j cap. In each of these cases, I want you to find out the magnitude of the vector and the proper angle like we have defined find the standard angle with respect to the x-axis in the anti-clockwise sense. So in that proper notation, I want you to find out the angle with respect to the x-axis. Okay, so anyone got the magnitudes in the first case? Waiting for your replies. So just substitute. So in the first one, you can see AX is √3 and AY is -1. So just substitute it that in the formula, you will get the answer. Correct. Angle beta, be careful. Okay. Now, why I'll say be careful? See, you look at the sign. AY is negative and AX is positive. So just visually think how the vector is looking. Is it looking like the vector I have drawn in the diagram above? No, because the above diagram is showing both AX and AY positive. So the angle theta is in the first quadrant. But the question I have given you, except for the second question, none of the angles are in the first quadrant. The first one, your y component is negative and your x component is positive. So that is falling in which quadrant? That's falling in fourth quadrant. So this is where our application of the trigonometry formula became important. Okay, so let's look at this. So if I'm just going with a formula based approach also, it's fine. I can still get the angle easily from that. So I can see that magnitude of A, yes, Ishita, your answer is correct. Okay. Magnitude of A is root of AX square plus AY square. So let's say I'm solving the E part. So it is square root of 3 plus 1. So the magnitude is 2. Okay. I can also see that tan theta is equal to AY by AX. So that is coming out to be -1 by √3. So tan theta is coming out to be -1 by √3. Now see, tan is negative. That means there are two possibilities. This is telling me that it could be in second quadrant or it could be in fourth quadrant. Now to figure out which of these two it is. So for that I have to understand that AX, which is A cos theta, is which kind of quantity? It's positive. And AY, which is A sin theta, is which kind of quantity? It is negative. So you can see that sin theta is positive, cos theta is positive and sin theta is negative. That is which quadrant? It is quadrant 4. So this information now has to be factored in. That okay, it is. So that's why my quadrant 4 is the correct one and quadrant 3 is. Okay. So now once we know that okay, it's in the fourth quadrant, we'll use the formula for the fourth quadrant. So for Q4, what is the formula for tan theta? Tan theta is minus of tan 360 minus theta. Okay. So here we'll use this formula. So this formula is telling me that tan theta, which is minus of tan 360 minus theta, is -1 by √3. So that means tan of 360 minus theta is 1 by √3. Okay. Just cancel off the minus sign. So that means 360 minus theta. And remember fourth quadrant, so 360 minus theta is an acute angle. So it's nothing but which acute angle? 30 degrees. So that means theta is how much? In fact, theta is 330 degrees. So this is where you have to be careful in your application of the formula. Okay. So I'm just minimizing this for you. We'll also understand this with a diagram, but better is you also understand it by how we can directly use the trigonometry in 4 quadrants formula. I mean, that is why we've invested a lot of time in that trigonometry in 4 quadrants, because it's very important to understand it from this whole vectors point of view, component algebra of vectors and general in vectors point of view. Okay, so if we were to draw a vector diagram here, let us see if that diagram justifies this or not. I'm getting this as 330, but let me also understand that my diagram should justify it. So my vector is drawing the supporting diagram here only. Was what it was, root 3 I cap minus j cap. If I just think of it in terms of how it's looking in the coordinate frame, with respect to my standard Cartesian coordinate system, the vector has an x component which is positive and root 3. So your ax is like that, and it is a y component which is minus 1. This is how the thing is looking. Your ax is positive of root 3, and your ay is minus 1. So naturally, where is your vector E line? Your vector E is lying over here. It is the sum of this and this. So it's lying here. It truly makes sense that the vector E is the diagonal of this particular side. So your vector E has a magnitude of the diagonal of root 3 and 1. So magnitude wise it is 2. But also you can see here that this angle is 30 degrees. Okay, so the angle it's making with the x-axis, we'll write as minus 30 if we are writing that way because it's clockwise. Or more properly, if we write, we'll have to write it this way, that it is this. Okay. So that theta is more probably plus 330 degrees in terms of proper anti-clockwise. So that is why we had got by the formula based method, because that's a formal way of showing the angle, we got it as 330 degrees. So this is something where you have to be very, very mindful and careful about the sign convention and all the various aspects of this. Now just quickly work out the second and third question, and with that we complete today's portion. Sorry, what was that again? I just check message. Yeah, I can minimize it. Correct. Drumi, your answer is correct for the second part. Ishita, your answer is correct for the second part. Ishita, hope you understood the first part, how the angle has come out, right? And Drumi, you understood how it's come out as 330. So this is definitely a little bit tricky. Okay, this part about the angle and all. Good. But with practice, ho jayega. There's nothing to worry about. You'll be working out an entire set of problems based on all these things. My worksheet as well as what you have in your module also, that will also help you. That will be more than enough practice. Okay. So let's come to the second and third part. Second part is pretty easy actually because both the components are positive, right? So second is almost direct. The second part you can see that Ex is +1 and Ey is also +1. So that means magnitude of the vector E is square root of 1 square plus 1 square or √2. And you can see that both are positive, so it's lying in first quadrant. So tan theta is 1 and it's in first quadrant. So that means theta is 45 degrees. And if you just make a quick mental diagram of the vector, it's very clear to you why that's the case. It's a vector like this of magnitude √2 and this angle is 45. It's very easy to understand why the components are +1 and +1. So that's simple. Now let's come to the menu is -12 I cap plus 16 j. So let's tackle this one. Okay. So Ax is -12. So that is telling me cos theta is negative. Ey is +16. So that is telling me sin theta is positive. So this is telling me that theta is lying in which quadrant? It is lying in quadrant 2. That's it. Okay. And now this information is showing me that the magnitude of the vector E 12 square plus 16 square. So you can take 4 common from both of them. So 3 square plus 4 square, which you know will give you 5. So this is 20. So the magnitude of the vector E is 20. 12, 16 and 20 are that same Pythagorean triplet as 3, 4 and 5. Correct? And now you can see tan theta is how much? It is minus of 16 by 12. Or it is minus of 4 by 3. And you already understood that theta is in the second quadrant. Okay. So use the formula of the second quadrant. In the second quadrant, we write tan theta as minus of tan 180 degrees minus theta. And that is minus 4 by 3. So that means tan 180 minus theta is 4 by 3. So that means now 180 minus theta is an acute angle because you've taken in the second quadrant. So we have just seen that this is happening for which one? This is happening for 53 degrees. Okay, that 3, 4, 5 triangle. So that means theta is how much? Theta is 180 minus 53 or 127 degrees. Okay. So I'll minimize this for you, and as you're going through it, just you can visualize the diagram also. This one is a vector which has components -12 I cap plus 16 j. So this is 12 and 16. So the vector itself should lie somewhere here. And that is why it is justified that its magnitude is 20. Also, you can see that this angle over here, it's just that tan theta is 16 by this, so this angle is 53. So naturally, it makes sense that the proper angle with the x-axis, this one, is 127x. Okay, so this is the complete solution for the C part. Okay, people. So with this, we complete today's portion. Now, before I wind up, just few more minutes. I want to just give you some quick hints for the worksheet, the second worksheet that I had given last time. We will do a full discussion of that worksheet questions in the next lecture. So first of all, there are a couple of corrections in the answer key of the worksheet. Actually, there are a couple of corrections in the worksheet. So I'll just put that up for you. So the corrections are, first question, the answer should be D. Okay, it should not be E. It's given in the back as, as answer key wrongly as E. The answer should be D. And there's one more correction, which is for question 15. Sorry, for question 13. In question 13, okay, it's saying that you have to find the angle between F1, F2 and F3, but actually it should be, the second line should be find the angle between F1 and F3. Don't find the angle between F2 and F3. Find the angle between, you can find between F2 and F3 also, but the answer will not match. Okay, so just change the line in the question. This is the answer. This is in the question itself. So just these couple of corrections. But now some questions I want to give you a hint about. Okay, so let's do that. So I think up to question number 6 you should be fine. They're direct formula based. Even 7. Let's go to question 7 is also fine. 8. Let's come to question 9. Now some hints. So in question 9, we have this situation. You're given that the angle between two vectors is an acute angle. It's 45 degrees. So you have two vectors such that the angle between them is given to you as 45. So this angle theta is equal to 45. This is given, but no other information is given. Okay. And now you have to compare. You have to compare the quantity mod of A plus B with the quantity of mod A plus mod B. Okay. You have to see whether it's larger, lesser than what kind of thing it is. Okay. So let's understand what we're doing here. So first of all, let's use the short form that mod A is equal to A and mod B is equal to B. Okay. So using that short form, you can see that magnitude of A plus B, according to this information that theta is 45, is becoming how much? It is root of A square plus B square plus 2AB cos 45. So further, it is becoming, substitute the value of cos 45 as 1 by root 2. So it's root of A square plus B square plus root 2 times AB. Isn't it? This is the value. So this is the left hand side of what you are comparing, the LHS. Okay. Now you want to compare this LHS with the right hand side, which was mod A plus mod B. So the right hand side, okay. Yeah, I'll repeat the error question. The right hand side is mod A plus mod B. Okay. Or you can just think of it as A plus B. Now, how are you going to compare this quantity with a plus b? Okay, so you can write a plus b in square root form. You can write it as square root of a plus b whole square. And when you expand this term, now you can compare these two very easily. You can compare these two terms very easily, and you can come to your solution. This will be a square plus b square plus 2ab. This is a square plus b square plus root 2ab. So I'm giving you enough hint to understand how to solve this. Okay? I will, if there's still difficulty in solving later, I'll help you out with this. But I would like you guys to try it out yourself using this. So this is about the 9th question. 10th, again, you can try out yourself. In 10th, my hint is draw the vector diagram. Draw the vector triangle and use geometry to solve it. That's it. The 11th question is actually very similar to the 10th one. In 11th, sorry, the 9th one. In 11th is given that magnitude of the vector A, which we can write in short form, is capital A is 12. Magnitude of B is 16. And it is given to us that theta is an, I think, an obtuse angle. Right? The angle between them is obtuse. Okay. So if it is obtuse, you know that cos theta, I don't know how much theta is, but I know it is obtuse. So the information I have from here is that cos theta will be some negative quantity. It's negative. So let us say it is minus of x or something, where x could be any fractional number like this. So now you have to compare mod of a plus b. You have to compare with 20. So just replace what is mod of a plus b. It is root of a square plus b square plus 2ab cos theta. And this thing. You have to compare this with 20. This is the left hand side. Okay. So as you can see, the right hand side, this thing, it is square root of 144 plus 256, that is 400, minus of, because this cos x is cos theta is a negative quantity, it is minus of 2 into 12 into 16 into x. Okay. Whereas this quantity, the right hand side, you can straight write it as square root of 400. So again, you can see on the left hand side, you have square root of 400 minus something. Why minus something? Because my cos theta is negative. So obviously it's going to be less than 400. So you can very easily compare the left hand side and right hand side. So this is how you do these type of questions where there's comparison involved. So that is just a small hint I wanted to give you. 12th is very easy. You will be able to work it out. You will have all these notes, so don't worry. You will be able to see these hints later. Now in 13th question, again a small hint I'll give you. It is given to us that magnitude of F1, and this is the one in which there is correction also, so I repeat that. So magnitude of F1 is 100 newtons. Magnitude of F2 is 80 newtons. And the magnitude of F3 is 60 newtons. Okay. And given to you that there's some, if all three forces act together on a given body, it's given to you that the net force on that body would be 0. So how you interpret that is that F1 plus F2 plus F3, this vector sum results in nothing. That's a null vector. Okay. So this is the meaning of this statement. So this is what is given to us. So from this, we have to find the angle, okay, between, in the question it is given F2 and F3, but change it to F1 and F2. So this is the correction, okay, change it to F. I mean, there's nothing wrong with finding between F2 and F3, it could have been that also, but your answer will not match. So this is the correction. Anyway, so now how will I approach this problem? Let's understand. So this statement over here, okay, this statement means that f3, for example, is minus of f1 plus f2. If I say a plus b plus c is 0, that means c is minus of a plus b. So that means vectors wise also the vector f3 is negative of the resultant of f1 and f2, which means that the magnitude of f3 will be equal to the magnitude of f2 plus f3. Oh, sorry, f1 plus f2. Just a minute, I'll just make a correction here. So this is equal to the mod of f1 plus f2. So when I take magnitude on both sides, the minus sign goes away. So this thing you know is root of f1 square f2 square plus 2 times f1 f2 cos theta. Now you see what all is given to me. f3 is given magnitude wise, f1 is given, f2 is given, and all I have to find out is theta. Okay, so that's all. So substitute in this formula and you'll get the answer. So these were the questions I wanted to give you a hint on. Again, question 14 and 15 are similar, you will be able to solve. Just if you approach these questions the way I'm telling you and continue ahead, you should not have too much difficulty. If you still require some hints and all, you can get back to me. But again, try to make sure you've given these questions a proper attempt, a very good attempt before we meet the next time. Okay. Plus, there will be a worksheet for today also, and that worksheet will mostly be to do with component algebra. All right, people. So that is for the end of today's lecture for me, and hope you understood everything properly. As I've told you before, you will be getting a video of this lecture as well as the whiteboard notes, okay, as well as a worksheet along with this. So make sure you revise everything carefully and properly and stay safe in the meantime. That's it for today.